Hello, everyone. This is a supplemental lecture on the role of pH in the LDH mechanism. So up until this point, the way that we've looked at the LDH reaction is represented here. So we've talked about how LDH can take lactate and NAD+, and it performs a hydride transfer to form pyruvate, NADH, and also a proton. Importantly, this reaction is reversible, so under different conditions, so for this forward reaction, we run this guy at a pH 10, but under other conditions, the reverse reaction, so LDH taking pyruvate NADH and H+, and turning it into pyruvate or lactate and NAD+, this can also happen under other conditions. But for our lab, we've been focusing mainly on the forward reaction. And so in the pre-lab lecture so far, when I've gone through and showed you the arrow pushing, the way that I've represented the arrow pushing is a base, specifically a basic amino acid, somewhere within the LDH active site has come in and plucked a proton off lactate. However, today we're going to go into more depth and talk more about what B is, because the identity of that amino acid, a conserved amino acid in LDH, and its protonation state, so whether or not it can perform the transformation of lactate into pyruvate, is highly dependent on the pH of the reaction. All right, so before I mentioned that the B, representing a basic amino acid, is actually a very specific amino acid, I was referring to histidine 195. And so you can see here that in the LDH active site, histidine 195 is deprotonated, so it's primed and ready for the LDH mechanism where it turns lactate to pyruvate. And we also have arginine 171 here, and you'll see why arginine 171 matters in a second. All right, so the first thing that happens is NAD+ binds the LDH active site, and that makes room for lactate to then pop in and stick into the active site as well. Now, one thing I will point out is that the way I've drawn the enzyme, so LDH here in this gray Pac-Man shaped blob, I've intentionally drawn it so the enzyme is closed around the reaction here. And that's intentional because what happens is after LDH binds NAD+ and lactate and anchors them into place, the enzyme's active site closes and it sequesters the active site from water. So water can't get in and it can't get out either. And that's really important for creating an environment in which a hydride transfer can occur. And that's something that happens in other enzymes that utilize NAD and NADP as cofactors as well. So once LDH takes up NAD+ and lactate, the histidine 125 and the arginine 171 are going to anchor that lactate in place. And this is especially apparent with the arginine residue. So it has that delocalized positive charge that can interact with the delocalized negative charge on the carboxyl of the lactate. And then once LDH has lactate anchored in place, histidine 195, that extra lone pair of electrons on this nitrogen, will go and pluck that proton off of the hydroxyl group on lactate. And so with a proton, that means we have an H+, so it's a hydrogen atom with no electrons. So it's taking off the proton, but not taking any of that hydrogen's electrons with it. So then there's all that extra electron density left on that oxygen. So those electrons are going to fold in, form a double bond. And then what's going to happen is this proton or this hydrogen atom is going to be transferred to NAD plus as a hydride. And so a hydride being a hydrogen atom with 2 electrons coming with it. And so as a result of that, we end up with a protonated and positively charged histidine 195. We have pyruvate, so that guy's gone, and then we have a double bond. And then we have NADH, so we've got 2 hydrogens there instead of 1. The double bonding pattern in the nicotinamide ring is going to change. That positive charge is going to go away, and we're going to end up with NADH. All right, so when we write down the products and the reactants of this reaction, you'll remember we have lactate, NAD+, is to form pyruvate as NADH, and also a proton. But when we look at the active site, we don't see pyruvate and NADH and a proton. We see pyruvate, NADH, and protonated histidine residue. So, and we know it's been pounded into your heads from the first and second lecture that as the LDH reaction proceeds, protons are released into the reaction solvent that then lead to the gradual decrease of the pH. So you know that happens, and you've seen it, and you've done the calculations, but if we look at the mechanism, it appears as if that proton is locked onto that histidine. But is that really the case? We're going to find out in the next few slides. All right, so this is what the reaction looks like at the end of the reaction cycle. So the enzyme has kicked pyruvate and NADH out of the active site. And as the enzyme is going to kick those guys out, the LDH is going to open up and expose those residues in the catalytic pocket, so specifically our protonated histidine 195, to solvent. All right, so instead of being isolated from water, there are now water molecules that are going to come into the active site and interact with those active site residues. Why is this distinction important? Because that catalytic histidine has a pKa of 6.7. And so what that means is when that histidine is exposed to water, so it's exposed to a buffer that has a pH of 6.7, half of the LDH population is going to have a protonated histidine 195, and the other half of the population is going to have a deprotonated histidine 195. So this population will be split half and half between protonated and deprotonated. However, whether or not the protonated state or the deprotonated state is favored can be determined by what the pH is. So we can shift the pH so one of the states is favored instead of the other. So if we take our buffer and we throw LDH in it, and our pH is very close to or less than 6.7, the protonated form of histidine is going to be favored. However, on the other end of the spectrum, if we increase our pH above 6.7, then that's the pH that we're operating at in our lab, so pH of 10, which is well above the pKa of 6.7, at this pH, the deprotonated form of histidine 195, so again, this is the form that can react on lactate, is going to be overwhelmingly favored. So what happens is after the lactate to pyruvate reaction has occurred, LDH opens up and it's released lactate or pyruvate and NADH. Water comes into the active site. And so again, our pH is greater than 6.7. In fact, we have a pH of 10. This histidine has a pKa of 6.7. So what's going to happen is the water from the solvent is going to pluck the proton off of the histidine, and we're going to end up with an uncharged deprotonated form of histidine 195. And so this deprotonated form is favored at the high pH, and then what that means is we have LDH that is primed and ready to take another lactate NAD plus into the site and start the reaction over and over again, either until we run out of lactate or the solution gets too acidic for the reaction to continue. So essentially, whether or not histidine 195 is in the correct protonation state to be able to perform the conversion of lactate to pyruvate depends on the pH of the solution and whether or not the pH is high enough that a sufficient amount of histidine of the population of LDH containing histidine 195 will be deprotonated. Now, the question is so we know that whether or not the LDH reaction, so the lactate to pyruvate, can occur is based on whether or not the pH is so that the histidine 195 is deprotonated whenever it's exposed to solvent so the reaction can continue. So what happens if we're at a pH of less than 6.7? So if we are at a pH that's lower, which form of histidine will be favored? Is it going to be the protonated form or the deprotonated form? And what does this mean for the reaction? Is LDH still going to be able to convert lactate into pyruvate? Is it instead going to favor pyruvate into lactate? Or is it going to do something else? And then finally, what's this reaction going to look like if we monitor it at 340 nanometers? Is it going to look like our LDH assays that we saw from labs 2 to lab 6, or are we going to see something a little different? And that's what I want you to be thinking about. I want you to be keeping that question in mind and go on your own and work on it, or work on it with your lab mates, help prepare you for the midterm and final exam. And as always, if you have any questions, please feel free to shoot me an email or schedule an appointment. Good luck, everyone.